Okay, so let's talk about the local versus the average heat transfer coefficient for the thermal boundary layer. So I mentioned, or we saw together this equation and we were able to derive it together. Now, the problem with this equation is that the temperature gradient is dependent on the location of where you're evaluating it at. And we said it changes along the path. So we know that this local heat transfer coefficient varies from point to point along the surface. And as mentioned previously, at a constant surface temperature, the temperature gradient decreases with x. Therefore, the local heat transfer coefficient is expected to continue decreasing until flow regime change occurs, but then it will continue decreasing after that. Because the wall temperature gradient varies along the surface, the local heat transfer coefficient also varies with position. So I'm saying the same thing again and again. Now, to characterize the overall heat transfer performance of the surface, an average heat transfer coefficient is defined. This is similar to the average friction coefficient, for instance. It follows the same philosophy. So what we're going to do is we're going to actually integrate. So that means we're going to take the cumulative sum of the local heat transfer coefficient over the whole length, and then we're going to divide by the whole length. In this case, it's the area. And this will give you an average number. Hello everyone, I'm Amr, a chemical engineer, been working in the engineering consulting industry for about 8 years now. My goal is to bridge the gap between academia and industry, between theory and practice, and give you the tools you need to succeed as an engineer. So if you want to succeed as an engineer, check me out. So the average heat transfer coefficient is obtained by integrating the local heat transfer coefficient over the entire surface and dividing by the total area or length for the case of a flat plate. In practice, heat transfer coefficients that you find from textbooks will be provided as average coefficients, not as local ones. The total heat transfer rate can then be expressed as the total heat transfer rate is equal to the average heat transfer coefficient multiplied by the surface area multiplied by the difference in temperature of the surface from the bulk of the flow. And by the way, I said that the difference in temperature is in the surface minus the bulk of the temperature. It doesn't matter if I subtract the bulk flow from the surface temperature or the surface temperature from the bulk flow. When I use these equations, I like seeing a positive heat flow. And so I like to always keep my higher temperature on this side of the equation to give me a positive number. But as long as you understand that heat is directional and you are consistent, then you should be good. Note that for the special case of flow over a flat plate, the local heat transfer coefficient only varies with distance x from the leading edge, and so the average heat transfer coefficient equation can be reduced to this expression. This expression is exactly the same as this expression, but for a plate, you are only concerned with the length, as the width will be constant and it can cancel out essentially. Okay, so we've already seen the variation of the local friction coefficient with distance from the leading edge previously. And I really like this image because it shows us the variation of the local heat transfer coefficient for flow over an isothermal plate. And as I've said before, the local heat transfer coefficient starts declining the farther you go away from the leading edge. And that's because, as I've mentioned many times, the gradient of the temperature evaluated at the surface of the plate decreases the farther you go away from the leading edge of the wall. And we said that that happens, one way to look at it is because the boundary layer thickens. And so we did find ways to reason through it. And also I said that, once you transition from laminar to turbulent, you have a spike in the coefficient, and that is mainly because of the turbulent mixing, which then produces a steep gradient. As if you remember, when we looked at the velocity profile for the turbulent flow, we had a flatter core, and as a result, we had a steeper gradient. And so this is also similar. When you have really good mixing, you will have a more uniform temperature, and so the bulk of the temperature gradient will be closer to the surface of the wall. So as long as you are aware and you understand this trend, that is what is important. So note that the trend is similar to the local friction coefficient discussed previously, and the distance xc over here is just the location after which the transition from laminar to turbulent begins. And this location is determined by the critical Reynolds number. So for a flow over a flat plate, this Reynolds number is known to vary between 10 to the power 5 to 3 times 10 to the power of 6. Okay, so now let's talk about the concentration boundary layer.